Hello everyone, and welcome to the first of a series of videos on the Solow Growth Model. Specifically in this video, we will be focusing on the production function, so on its shape, its components, and its properties in general. To start off, what is the Solow Growth Model? Well, if we really want to give it a definition, we can say that it's a tool. It's basically a tool that allows us to understand long-term economic growth, which is quite important, of course, on a macro perspective. And looking at the production function, this is the perfect item that is going to allow us to begin implementing our model. What we mean by production function, we mean a tool that allows us to combine capital and labor in order to obtain output. So it shows how capital and labor combine to produce the final amount of output. To put it into a mathematical equation, we could easily describe it as yt, so output at time t, being equal to this function that, as we said, combines capital and labor. And this function could have different forms, but for now, let's leave it in general terms. And for the purpose of this simplification of the Solow growth model, of this introduction, let's assume that there is this total factor productivity term, this let's say, technology term that is assumed to be exogenous. Note that when we say exogenous, we mean that it's something that is not actively determined within the model, but it's as if it's given in general. It's given to us as it already is, and we just need to implement it. So this production function is basically an equation, right? And as every equation, it has some properties. Some very important properties that allow us to map it and to describe what this production function does. First of all, the first derivative of this production function is going to be greater than 0, so it means it's going to have an upward sloping, it's going to be an upward sloping curve, it's going to have overall a positive slope. However, it's not going to increase in a linear way, and we're going to see in a moment what we mean by that. Graphically speaking, but it's going to have a decreasing rate. So the second derivative is going to be less than 0, meaning that the slope will be positive, yes, but the slope will be increasing at a decreasing rate. And this is crucial, this is really crucial to understand why this is the case and how it is the case. So we said that we need capital and labor, right? Let's begin by mapping how capital relates to the final production function. So the curve is going to look like something like this, because as we can see, it has a positive slope. So yes, the first derivative is greater than 0, as we've already said. However, the slope is not going to increase at a constant rate. But as we can see, if we try to map the slope as a tangent to a point in the curve, this slope itself, this gradient, is going to be different at every point. And specifically, it's going to be decreasing because, as we can see, the tangents become flatter and flatter. Well, why is it the case? So now we've looked at the math, what is required for this output production function to let's say, show this shape mathematically speaking. However, it's also important to give an economic meaning to all of this. And this is where marginal products come into place. So what are marginal products? Well, in order to identify the marginal products, we need to take the first derivative of the production function with respect to capital, for example, or with respect to labor, depending on what marginal product we want to identify. When in general we talk about marginal product, we refer to the, let's say, additional output that we can gain following a marginal increase into our input. So how is this calculated mathematically? Again, with the partial derivative. So if we take the partial derivative of the production function that combines capital and labor with respect to capital, then we are going to have our marginal product of capital. which can be interpreted as measuring. It basically measures, so it measures how much more output would change. So it would increase, how much more output would increase or how much output would change following a 1 unit change in capital. And here comes the important bit, keeping labor constant. Okay, so let's slowly unpack and analyze this statement. So we're saying how much output would change. So how much will our production function predict output to increase or decrease? But in this case, we know increase, since we know we have an upward slope into our production function, following a marginal change, a 1 unit change in capital, which is why we are taking the partial derivative with respect to k, keeping labor constant. So in practical terms, if we think about it, let's say we have something like 4 machines or 2 machines, actually, let's start with 2 to produce, I don't know, 2 pizzas. So we have 2 pizzas to be produced with 2 machines. And each machine has 4 workers working on it, right? So what happens if we add 1 machine? We would have, well, 3 machines. Makes sense. However, we're going to have the same amount of workers on it. So we're still going to have 8 workers as before. So they're just going to be distributed in a bit of a different way in this case, because as we said, we are keeping labor constant. We are not changing our labor, because otherwise, if we were to simultaneously change the amount of workers that we have into our production process, we would not be able to identify the effect of capital itself. So what this marginal increase in capital would provoke. Hence, what would the outcome be? Well, now, yes, we have more machines, so for sure we might be able to produce more pizzas. But are we going to be able to produce that much pizza, as many pizzas as the increase before ours? Let's say we are able to produce 3 pizzas in this case. Well, for sure, maybe the next time that we introduce an extra machine, the next extra machine that we introduce, so adding, without adding any more labor. So we're going to have the same number of workers, which in this case we said it was, well, did I put 7 workers here? It should have been 8. Yes, here we go. This is good. So if we still have 8 workers and 4 machines now, we're only going to have 2 workers per machine, because 2 are going to move, right? And as much as we like it to have more machines, we are not going to be able to use the machines at their full capacity. Reason why we're not going to be able to increase our output as much as we did before. Before we were able to produce a full entire extra pizza, but now maybe we would just be able to produce, I don't know, 3 pizzas and a half, which is quite sad, because just because these machines, these maybe ovens that we're using to make the pizzas, they are not used at their full capacity, since we are not adding any extra labor. But this, keeping the amount of workers constant, really does allow us to identify the effect of increasing capital on output. So this is why it's very important to understand this relationship. And as we said this for capital, we can say the same thing for labor. So I've already written down the definition for you. So keeping capital constant, it measures how much output would change following a 1 unit change in labor. And again, this would be calculated taking the partial derivative with the production function, but with respect to labor instead this time. Some of you might be wondering why we only keep capital and labor and we don't consider other factors of production, such as, I don't know, land or enterprise. Well, let's say that it's a simplification. It's a simplification of the Solow growth model. Right now, of course, you could incorporate different factors, but this is going to be explored in later videos when we're going to have all the full setup of our Solow growth model laid down already. So one tiny note for you is to remember that when we take a partial derivative with respect to a variable, um, we have to treat the other variable as a constant, of course, because otherwise we would not be identifying, as we've extensively said, the true effect of our increase in the factor that we are analyzing. To continue with, let's summarize the little law that we've said and give it a name. So basically, we just described the law of diminishing returns, which states that and is described by the gradient of our curve. So since the gradient of our curve is decreasing, we're not saying that the slope is decreasing, we're saying that the gradient is decreasing. So the slope is increasing at a decreasing rate. So the gradients, it's as if it's the rate of change is decreasing. Hence, every time an extra unit of capital is added, it is less and less valuable because it does produce less output than the unit before, for the little explanation that we've already said. This leads us to making two main assumptions and looking at two main assumptions that are going to be crucial for our description of the Solow growth model. First of all, we are assuming only two capital of production, or only two factors of production, so capital and labor, which again, it's a simplification. Hence, the production function that we have does show how to combine these two inputs, and it's an incredibly powerful tool to obtain output y. If we were to give a form to this production function, for example, it could be something like the Cobb-Douglas shape, where we give a power, so two powers that add up to 1 to our two factors that multiply each other. And in this case, these two little exponents here that we have, so alpha and 1 minus alpha, would give us the share of each factor input that is required in the production of output. So this is just, again, an example. It doesn't have to be the case, but it's very often the case that Cobb-Douglas is used as a, let's say, shape, as a form for the production function. And why are these the shares? Well, because if we take, for example, the log of this whole equation, so if we take the log, we could break it down according to the laws of the log. So we could easily say that this is equal to log of k to the alpha plus log of L to the power of 1 minus alpha, because we know that if we have a multiplication between two terms within a log, that is going to become a summation. We could sum the individual logs. And again, we could move the exponents as some kind of multiplicative coefficients outside of the log parenthesis, again for another law of the logs, so that we would end up having something like a log k plus 1 minus a log L. And as you can see in this case, the alpha and the 1 minus alpha would be the shares, because it's like they are proportions. They are multiplying the amount of factor of production that we are using. So this is the first big assumption. So we are only having two factors of production, while our second big assumption is going to be that investment is a constant fraction of output. And this is crucial. We are saying that the saving rate is constant as well. And it's going to be and this is going to be an exogenous factor. So keep in mind that this exogeneity is fundamental, and we are going to explore more of it in the following video. I will see you soon in the continuation of this topic.